Hello and welcome to the October 2023 Longevity Review, presented to you by the Canadian Longevity Association, a federally incorporated nonprofit whose mission is to help accelerate the introduction of effective longevity treatments and to ensure their free availability to all Canadians under the healthcare system. My name is Chris Linnell, and I'm the founder and president of the association. We are a volunteer-run organization and are always looking for more help. So if you'd like to assist us in achieving our goal, then please get in touch via the links below this video. In addition, you'll also find a link to the newsletter being discussed here. This month, we will take a look at how exosomes taken from young pigs cross the species barrier and were able to potentially rejuvenate old rats, how a small molecule helped regenerate the damaged tendons of older rats, the big implications of a post-conception rejuvenation event in human embryos, and how it is never too late to gain muscle mass and strength via resistance exercise, even if you are older than 85 years. Okay, let's get stuck in then. So on to the first paper we're going to look at. But first, a disclosure. So I've been following this research pretty much since it started, and I know one of the principals behind it, who is actually a longtime reader of this newsletter, so just a potential bias alert. But looking at this paper now, it's almost a little bit too good to be true, but incredibly exciting. Now, the fact that Steve Horvath, you can see here, first author, has put his name to this paper gives it a lot of credence. Now, Steve Horvath was the inventor of the original epigenetic clock and is probably going to win the Nobel Prize at some point. So the fact he's put his name to this, as I say, gives it a fair bit of credence. Now, a bit of background to this research. The researchers initially started off by transferring young rat plasma to older rats, which had some remarkable effects. Subsequently, they've reduced the plasma to a fraction, which also had quite substantial effects. And in this paper, they've revealed that that plasma fraction mainly consists of exosomes. Now, exosomes are sort of these small spherical packets of chemical information which cells use to communicate with each other. And so they've taken young exosomes and given them to older rats. In this research, they've moved to taking the exosomes, or the plasma from which the exosomes come, from young pigs and given them to rats, older rats again. So this potentially shows that it can cross the species barrier, because it'll be a bit difficult to get lots of exosomes from rats, considering how small they are, whereas pigs are a readily source of this material. So let's take a look at the research. So they started off, first of all, by developing some specific epigenetic clocks for rats, and also some pan-epigenetic clocks for both rats and humans. And the first figure, we'll take a look at when I get to it, simply shows the validation of these clocks. I won't go into the details, but you can sort of see these lines between the age and their sort of chronological age and their epigenetic age, and the fact that they all sort of seem, these dots seem to cluster along a line, indicates that there's an accuracy, that they have a certain degree of accuracy. Now, once they developed those clocks, they then as they took the blood from 6-month-old pigs, extracted the exosomes, and gave them to 18-month-old rats in two injections, I guess you could call it, one from 0 and one after 96 days. And then 150 days later, they sacrificed the animals and did the methylation assays, which basically gives you the epigenetic age. And as you can see from these initial graphs here, so firstly, on the left, we have the old, on the left in red, the old rats who only a sham treatment was given to. The blue middle column is the young, forget how old now, six-month-old rats or something like that. And on the right, the sort of the orange bar are the older rats who were treated with the exosomes. And each of these sort of bar graphs represent different tissues. So we got blood, liver, heart, hypothalamus, and there's sort of 3 different clocks were tested. And for all of these, you can see that there is a substantial difference between the old rats on the left and the right, the old treated rats on the right, with their epigenetic ages return pretty much very close to that of the younger rats. Less so within the hypothalamus, which is a region of the brain, but still there was a substantial reduction there as well. And regardless of the clocks used, so there's pan tissue, so for all tissue, specific blood clock, and a human and rat pan tissue clock. For all of these, you can see this quite substantial reduction in epigenetic age, and as I said again, closely approximating that of the younger rats. Now, this is all sort of nice and well. There's still a lot of questions about how much epigenetic age actually correlates to actual aging, and if by reducing epigenetic age actually makes a difference to the sort of the real age of the animal, the biological age of the animal. So we'd like to see more than just an epigenetic age reversal. We'd like to see some physiological changes in the animals, and that is what the researchers did. They tested various parameters. So let's take a look at the next set of figures. So once again, in all of these charts, the red dots represent the old untreated rats. The blue dots represent the young untreated rats, and the sort of the yellowy orange dots represent the old treated rats. And this first line here deals with markers for the liver. And as you can see here, after treatment, you can see days post-treatment from 0 to 150. All of the markers for the treated rats started moving towards the levels of younger rats. In some cases, after 150 days, they reached the same level of the younger rats. So this is, again, a demonstration of the function of the liver. So it looks like the liver sort of rejuvenated to a degree. The second line here deals with cardiovascular parameters, I guess. So triglycerides, high-density lipoprotein, cholesterol, and glucose. And once again, you can see that the orange dots progressed towards the younger rats over the course of 150 days. In some cases, equaling it exactly. And here at the bottom here is the last line is about kidney function, so creatine, bun, and total protein. And once again, we see that the orange dots started moving towards the levels of the younger rats. So pretty impressive results so far. Next, the researchers looked at cognitive function. And next chart. So once again, blue being the young rats, red being the old untreated rats, orange being the treated older rats. And here they tested the cognitive function by using the Barnes maze test, which is sort of rat is placed on a circular platform with all these sort of escape holes dotted around, and they need to sort of learn which hole is the way to escape from the open platform, because rats hate being exposed and out in the open. And so the first, they tested them 4 times. Each test lasted sort of 9 days of training. So the rats were meant to improve over the course of those 9 days of training. And you can see at the bottom here is how many days post-treatment. And at the beginning, the treated rats were the same level as the older rats, but they improved. So on the left axis here demonstrates how many seconds it took for the rat to escape from the open platform. And as you can see here, there was a statistically significant divergence between the treated rats and the older rats. Second set of tests, once again, the same result occurred, and getting even a bit closer to the younger rats. Now, the treated rats were given a second injection after 96 days, and so third and fourth tests took place after that second injection. And as you can see here with the third test, the treated rats already were starting at a lower level, or they were a faster escape, you could say, than the older rats. And basically, the third and fourth one progressed down to pretty much, pretty much to the level of the young untreated rats. So again, indicating that their cognition improved substantially here. Next, the researchers took a look at markers of inflammation, sort of oxidant and antioxidant markers. So malonyaldehyde, MDA, stick it to that, is a marker of oxidization. So we want lower levels of that. And once again, in 4 different tissues, brain, heart, lung, and liver. Again, red being untreated rats, orange being the treated rats, blue being the untreated young rats. Once again, the levels of this oxidant dropped considerably and returned to levels fairly close to that of the young rats after 150 days. Now, reduced glutathione is an antioxidant, a naturally produced antioxidant in our body. So we want higher levels of that. And once again, the levels in the treated rats are substantially higher than those of the untreated rats, and again, started approaching the levels seen in the much younger rats. Catalase and superoxide dismutase, once again, are antioxidants in the body. And as you can see here, there was a substantial difference between the old treated and old untreated rats, once again approaching those levels seen in the young rats in all 4 different tissue types. Next, they looked at markers of inflammation, of chronic inflammation. And a couple of those common markers are interleukin-6, IL-6, and TNFA, tumor necrosis factor alpha. And you can see here that the rats started, the old treated rats started pretty much the same level as the old untreated rats. And after a very short period of time, inflammation markers dropped down to the level of younger rats. Then after a while, they started rising again in the treated rats. But then after 96 days, again, they were given a second injection after 96 days. The levels once again dropped and actually went below that of the younger rats. Same thing occurred with TNFA, starting off pretty much the same level as the older the untreated rats, decreasing, not quite to the level of the younger rats before rising again, but then after the second treatment, falling down once again and actually reaching the level of the younger rats before the animals were sacrificed. And finally, NRF2 is a master regulator of detoxifying enzymes. And once again, we'd like higher levels of that. And once again, in 4 different tissue, brain, heart, lung, and liver. The levels in the old treated rats after 150 days were substantially higher in the different tissue, apart from the lung for some reason, than the untreated rats, once again closer to the levels seen in the young untreated rats. Now I have no idea why why the lung sort of stood out, but nothing is perfect, I guess you can say. But so, as I say, very impressive results so far. And next, they also tested the glycans in the rats. Now, glycans, glycan aging, it says there, glycans are sort of proteins found on the surface of cells, and they change over the course of aging. You can actually get a glycan age test. And here we've changed colors. So in both of these graphs, on the left we have the untreated control. The red is the treated older rats, and the figure on the left is a marker of inflammation, a pro-inflammatory signal, which rose with the untreated rats but declined in the treated rats. And the second marker, G2 here, is a marker of anti-inflammatory action or something like that, which decreased in the older rats, but increased once again in the old treated rats. So in all of these tests they did, there was a substantial rejuvenation of these older rats. And in fact, in unpublished research, they did a lifespan study of the rats, and one of the rats supposedly is the longest lived rat ever recorded. I mean, that was an incredibly small study. I think of only 6 rats, so big asterisk needs to be placed next to that result. But again, very promising. I should also mention that not a huge number of rats were used for these experiments, but I mean, the results just sort of completely stand out. And I know that reading an interview with Steve Horvath when he was initially approached to do some epigenetic testing, he was blown away by these results, and he's very excited by this. And I communicated again with the friend I know, and I was told that they are next moving into trying this out in dogs, with that experiment starting early next year, once again using pig's blood. But also, as an aside, speaking to someone else involved, that there was a huge difficulty in actually finding the appropriate blood from pigs, especially in the USA, because they needed pigs that were not on antibiotics, fully organic, no growth hormones or anything like that put into them, which were difficult to source. And secondly, it was actually difficult to extract the plasma because there was so much fat in the pig's blood that it clogged up the machines. But yes, the other significant thing to mention, of course, is that there's been talk online or read popular science stories about vampires and how people are trying to use young blood from people, and like Brian Johnson used from his son, which of course raises huge ethical concerns. However, the exciting thing here in this research is not only the results, but the fact that it was from pigs in rats. The species barrier was crossed to get these results. And if young pig plasma or young pig exosomes could rejuvenate older rats, there exists the possibility that young pig plasma or young pig exosomes could rejuvenate us as well. So very excited to look forward to the research in dogs. I mean, if they prove it, if they can rejuvenate dogs, well, that's a major step forward. And the next stage after that would be testing it in humans. So definitely a case of both fingers crossed about this research, because if it pans out, this could be big, incredibly big for us. Moving on to the next paper, which is all about repairing damaged tendons. Now, damaged tendons are a major source of disability or an inability to conduct exercise, especially sort of resistance exercise, and are more common in older people than young. And also tendons repair themselves very slowly, even in young people, even worse so in older people. And if that healing process could be speeded up or be more successful, then that hopefully could mean that people could engage more in not only in exercise, but just in general activities of daily living, and hopefully maintain their strength and reduce their chances of becoming frail and being basically aging more successfully in older age. Now, the researchers here employed a deep learning methodology to screen various molecules for their regenerative capacity, and by looking at sort of the signatures of regeneration, looking at the Yamanaka factors actually. And let's take a look at their first graph here. I won't go into the details of how they utilize machine learning, because that is yeah, that's beyond my pay grade. But they found a molecule called primoglucosalcimifugan, or POG. I'll stick with POG, I think, which had the greatest effect. And you can see the chemical structure of POG. And first they took tendon cells from young rats, young 3-month-old rats, and in a Petri dish, either just gave them control, which is the DMSO, or they gave them the POG. And here the first pictures show their proliferative capacity, so greater extent with POG. Yeah, CFU is colony forming unit. So basically when things regenerate, they first again, once again, the specific details are a little bit beyond me at this stage, but you can see here more CFU is better, and those young rat tendon cells displayed more of that. Also Ki67 here, that's a type of cell, a progenitor cell, so not quite a stem cell. They reproduce and produce different tissues, but sort of in an organ-specific context. And so once again, the cells treated with POG had a higher percentage of these Ki67 cells, which again show greater proliferation. So here are the two Yamanaka factors that enhance proliferation, SOX-X2 and OCT4. Once again, they increased in the POG, the POG-treated cells. SA beta gal is a marker of senescence, so we want less of that. And once again, the markers of this were lower in the POG POG-treated cells. See here on this graph, quite a bit lower. So the pink is obviously the treated cells. And markers of inflammation, so IL-6, TNF-A, which we had in the previous study, and IL-beta, once again, substantially lower in each of these in the treated cells. So here are next we have markers of tendinocytis, or getting my words all screwed up here, but basically these are markers for proliferation in tendons. They're growing, and again we're quite a bit higher in the treated cells, or depending on what was being looked at here, the lower or higher, but these are all good results. Next, they implanted these treated cells in a collagen sponge in a sort of a mouse model. And again, TNC, TNMD are markers of tendon growth, I can say, you could say, and they were substantially higher in the treated cells. And if you look at just these two sort of cross sections of this collagen seeded sponge, or the cell seeded collagen sponge, quite a bit denser for the treated cells. Next, they moved into whole animals, and they they did that, but they also they moved into, rather than using 3-month-old rat cells, they used 18-month-old rat cells, so rats who were sort of in late, middle, or early old age. And similar to the previous previous figures, you can see here that unlike the 3-month-old rats, the untreated older rats had much lower levels of the CFU, whereas the treated rats had way higher levels. You can see also by this graph here. Likewise, with these Ki67 progenitor cells, higher in the treated animals. Levels of SOX2 and OCT4, once again higher in the treated animals. But why do they change the color? I don't know. Again, markers of senescence decreased as well. Markers of inflammation decreased as well. These markers of tendon growth, let's keep it simple, increased in the treated cells. So this is all done in Petri dishes once again. But they then moved on to treating whole animals, and you can see the study design here. 18-month-old rats. They were systematically given this POG for 2 months, starting at 18 months, and after 20 months, they had their I guess hind limb tendons partially cut. No, so not a full cut, but a partial cut. And then they were analyzed after 1 and 4 weeks later. And so the tendon self-healing capacity. So here, mark sort of cross sections of the tendons, and little white dots you can see are fat deposition in the older animals. And that's one problem actually we have when we get older, is that fat starts not only accumulating around the tummy and various other places, but also within our muscles and within various organs and things like tendons, which we don't want. And you can see here that in the treated animals, much less, if any, fat deposition. So lipid positive areas substantially lower. And these CD146 plus cells, again, which are markers of proliferation, increased, were substantially higher in the treated animals. And you can sort of see from this cross section, it's much sort of denser than in the control animals. Next, the researchers, rather than systematically administering this POG, they looked at local delivery. So these maybe it's not beneficial to have it circulating throughout the entire body, but just localize it around the tendon injury. So they developed some nanoparticles which they could inject near the site of injury, which here basically 1 day after the surgery, they were given an injection, and a second injection after 2 weeks, and these nanoparticles slowly released the POG, as you can see on this line, over the course of 16 days. And once again, when they examined the tissue of the treated rats, so I guess after 4 weeks, once again, there was an increase in these progenitor cells, the Ki67s, increase in markers for tendon proliferation, the TNC, a reduction in sort of fatty deposits, an increase in the CD146 cells, a decrease in these, I forget what these cells are now, but decrease in these, which is a good thing. And yeah, various other analyses showed an improvement. Can't remember what all these things are, but yes, basically there's basically substantial, statistically significant, shown by the 2 stars or the 3 stars, depending how statistically significant the results are, between the untreated animals and the treated animals. Next, the researchers looked at what happened when the cells were stimulated with an inflammatory molecule, in this case TNFA, which we've seen in prior studies. And here, so they took cells. This time I think it was from younger rats again, but they were either stimulated with TNFA or not. And you can see here in terms of colony forming units, those cells given TNFA had a decreased number, whereas those who were treated with POG had higher levels of them, almost approaching those of the unstimulated cells. Similar thing occurred with senescent markers, because TNFA is something that is secreted by senescent cells. And the untreated cells have much higher levels of senescent markers compared to the POG-treated cells. And once again, I forget what the staining. Yeah, so this how much TNFA was in the system or in the cells. I guess the staining is showing what isn't, what doesn't have TNFA. Again, the levels of the treated animals was comparable to that of the control, unlike the untreated cells. And also here again, marker of tendon cell proliferation. The TNFA treated stimulated cells had much lower levels of this, whereas the ones which also were given PLG had much higher levels, which is a good thing. On to the next experiment they did, and this involved looking at autophagy, and which they decided, realized was probably the main reason, increased autophagy, which is, by the way, when sort of the self-eating or the recycling process within cells. And usually we want more autophagy, not too much, but we want more autophagy because that keeps the cells all nice and tidy and in good shape. And they're looking at how mTOR was impacted. Now, mTOR, mechanistic target of rapamycin, when the levels of that are higher, autophagy is lowered. When mTOR is lowered, autophagy increases. And they basically, PS6 cells are sort of are downstream regulator of mTOR. And again, in the treated cells, it was much lower than in the untreated cells. And they looked at this on various different levels. Won't go look at this too closely, but once again, in all these tests that they did, the treated cells were much better than the untreated cells. Now, next, and this is where it sort of gets more interesting again, is that they next took cells from humans, older humans, though older humans around 50 years of age. Now, I take a slight bit of umbrage at this depiction of a 50-year-old because that looks it looks a bit too old for my liking, considering that I'm swiftly approaching 50 myself. But they had supposedly issues with obtaining tissue samples from older people, especially since, again, the issue is that getting tissue samples from people whose tendons heal even worse is maybe not the best of ideas. But anyway, they took tendon samples from, again, people in their 50s and treated them in the Petri dish once again. And just like the results in rats, we see an increase in these proliferative Yamanaka factors compared to controls. I don't like the fact that they keep on swapping the color here. In this case, it's black is the treated cells, and pinky purple are the untreated cells. Again, there's an increase in the CFU. There's an increase in the proliferative Ki67 cells. A decrease in the senescent cells. See the markers here. A reduction in inflammatory markers. And what else? Yeah, again, an increase in these tendon growth factors, TNMD and TNC, with a substantial increase in both of them. And these PS6 cells, again, this is to do with mTOR, a decrease in those cells as well. So this is quite interesting how that seems to work in human cells the same way it worked in rat cells. And sort of finally, they then looked at what happens when a tendon is completely cut, so surgically sliced apart, and they don't really grow back together again properly at all. So regardless of, I guess, stimulation by POG or what have you. So they developed a bioscaffold, which you can see are sort of images of, to help and seeded them with the tendon cells, also treated with POG. So the mice were once again orally administered it, so it was a systematic administration of this POG rather than localized. And yeah, so they had their, as you can see here, their tendon, big section chopped out, replaced by this seeded scaffold, and then they were harvested after 12 months, and they were examined, and there's also a functional examination we will get to. And here you can see sort of a X-ray, not sure exactly what, showing how much bone or sort of how much calcification occurs. I guess another issue, and apart from fat turning up in places we don't want it, bone turns up in places we don't want it when we get older. And what this is showing is the sort of the bone deposition within the tendons. And on the left we have 3-month-old rats, and there's pretty much no bone there. The 18-month-old rats, untreated rats with POG, shows a substantial amount of bone growth there, whereas the treated rats is pretty much none. And the normal here shows just, I guess, how in older rats you start getting bony substances appear in your tendons. And here's the graph showing the difference, how the untreated animals had much higher levels and the treated animals lower levels of the sort of bony disposition. Next, obviously, they also want to find out what
this results, what are the real world results of this. And here they saw what sort of mechanical loading the hind limbs, which were the treated limbs, on a plate, and just looking after 8 weeks, here we got 3-month-old mice, 18-month-old untreated mice, 18-month-old treated mice, and I guess they've got much bigger footprints, so to speak, quite approximating for the treated animals those of the sort of the normal 18-month-old mice, sort of rats, who did not have their tendons sliced open. And sort of Achilles function index after 8 weeks. The middle bar here are the older untreated rats, and the bar on the right is the older treated rats, again approximately those of the 3-month older rats. And similar with grip strength, on the right is normal undamaged rats. On the left are the damaged untreated rats, and the one in the middle are the damaged treated rats. And although their grip strength improved from that of the untreated ones, it didn't quite reach the levels of the uninjured rats, but certainly it's heading in the right direction. And here are just sort of some cross sections of the tendons afterwards, and you can sort of see here, I mean, it's difficult to tell, I'm not an expert in these sort of eyeballing these things, that the top level are the 3-month-old rats, middle level are the untreated old rats, lower level are the old treated rats. And just looking at the pictures, you can see that they seem to be closer in appearance to the younger animals than the untreated animals. So yeah, quite interesting. That was the last one, and just finishing off by looking at a schematic for the overall experiment. But basically, it seems to show that this molecule could really improve the healing of tendons, and hopefully that would lead to greater functional recovery for older people, and increase their ability to go back to exercising or just daily living. So this gives us hope that we will be able to recover faster in the future from any tendon injuries that we unfortunately receive. Now, the next paper we're going to look at is more theoretical in nature when it comes to longevity, but as I said in the intro, has very big implications. And it seeks to sort of answer, or perhaps provides the answer to the question of, why are we born young? Now, when you think about it, we all came from a sperm and an egg, but the sperm and the egg came from older individuals. What didn't come from 0-year-olds. They came from, well, in my case, my parents were in their mid-30s. So the ovary which produced me, was formed in my grandmother's womb. But I did not come out looking like a 30-year-old. I came out looking like a newborn, as all newborns do. Now, something needed to have happened to have sort of, in a sense, reset the clock. And the researchers here, led by the esteemed longevity researcher Vadim Gladyshev, initially produced a paper a couple of years ago whereby they used epigenetic clocks to looking at how mouse embryos sort of develop over time, and they sort of tested their epigenetic age at various points, and they found out that at conception, at fertilization, the age was sort of higher than it was a short while later. The epigenetic age reduced, and they surmised that that was sort of the point at which, in a sense, our aging clock started ticking. And but that was in mice, and maybe assume that the same would be in humans. But of course, they needed to find that out. Anyway, this paper looked at the same process in human embryos and basically replicated the results found in mice. Now, there's only one chart to look at here, a graph, so to speak. I can make this bigger. And so they use different data sets, I guess tissue samples or what have you. And so data set 2, 3, and 4. I don't know why. I'm not sure why there's no 1. But anyway, here you can see these 3 data sets. The bottom axis shows different stages of embryonic development. And the left axis shows the epigenetic age. It says in years. I'm not sure why it says 25, 50, 75. But anyway, higher means older. And at conception, or shortly after conception, the epigenetic age was, well, was up here, sort of fairly older. But then there occurred an event at which the epigenetic age dramatically decreased before starting to rise again. And the same held true for all 3 data sets. You can see this drop here in the first one, this drop here in the second one, and this drop here in the third one, even though it's saying 4th data set. And according to, you can see these NSs, NSs, and then these stars. NS means not significant, whereas the stars indicate a greater degree of statistical significance. And the more stars, the more statistical significance. And as you can see, each of these drops, there were, well, 4 stars, which signified statistical significance in this change. Now, the researchers don't know exactly what caused this, and but almost, hold on, let me just say that again. The stage at which this happened was sort of like 3 weeks after fertilization, when the tiny embryo implants itself into the womb, and it goes from 2 layers to 3 layers. I must admit, embryology is not something that I am very, very familiar with. Regardless, there appears to have been a rejuvenation attempt where all that sort of damage or issues with older cells was cleaned away, and you know, a newborn could be born newborn. And for me, this is very significant. I'm sort of a bit surprised this paper, these papers haven't sort of received more attention, because although we don't know exactly how this occurred, the fact that it did occur means that we should be able to figure out what caused it and hopefully apply that to us older individuals. As I say in the text, you know, if we've been rejuvenated once already, why can't we be rejuvenated again? And so that's why I think this has very big implications, at least at a theoretical level, and gives hope that rejuvenation is not a pipe dream, since nature seems to do it all the time with every single generation. So it's exciting. It'll be interesting to see where this research leads and whether or not they or other researchers can unravel the mechanisms behind that and hopefully apply it to us. Okay, on to our final paper that we are going to look at. And this is where previous papers are about the future. This paper is about the here and now, what you can do if you are an older individual to improve your health. And that involves exercise. Now, and specifically resistance exercise. Now, some people worry that as they get older, they won't be, there's almost no point in doing a resistance exercise because they're already old. It won't make any difference and all that. However, this paper proves that that is not the case. Say proves is maybe too strong a term, but still, it strongly indicates that this is not the case. Now, this was a very small study, only around, how many people were involved? Right, 17 and 12, so like around 30 people were involved in total. Took place in Chile. They had issues with COVID to get up to the requisite number. And so yeah, 17 older adults. And so the two groups, there were one group, the first group was people between the age of 65 and 75. And the second group were people over the age of 85. And both sets of people performed 12 weeks of resistance training. This was 3 times a week, whole body, so all parts of the body were trained, and it was also progressive. So they started off at 60% of their maximum, sort of, well, 1 repetition maximum, and that progressed up to 80% of their one repetition maximum. At the halfway point, they were tested again, and once again, because their strength increased, they went from 60 to 80% of their 1 repetition maximum for the final 8 weeks. And only a couple of graphs, take a look at. Let's look at this first one here, view full size. And okay, so the white bars on the left are the 65 to 75-year-olds. The grayish bars on the right are the older than 85. And this talks about, this shows the quadriceps muscle CSA, cross-sectional area. So basically their muscle mass, how big their muscles are. And the quadriceps, I believe, are in the legs. And you can see here just by eyeballing it that for both groups, there was an increase for pretty much everyone. You can see here going up, but in percentage terms, what did this mean? It meant that roughly just under 10% increase for those 65 to 75, and I believe 11% increase for those over 85. So the oldest increase their muscle mass in terms of percentage just as much, if not more, than those slightly younger individuals. Obviously, there's a 10-year gap between both groups. So, very positive results here. Get out of here. And secondly, but how does muscle mass translate into strength? It's not how big you look, it's what you can do that matters. And here they looked at the strength of sort of 1 repetition maximum leg extension strength, and also a timed up and go, where how quickly can they get up and go, I guess. And once again, on the left are the 65 to 75-year-olds, on the right are the 80 plus 85-year-olds. And in both cases, pretty much for everyone, it looks like, their how much they could increase their strength. Well, they all seem to be able to increase their strength. Now, again, there was a 10-year difference between both groups. So the over 85 started at a much lower level than the 65 to 75-year-olds. And, even after 12 weeks of training, their level did not reach that of the untrained 65 to 75-year-olds, but still there was an increase. And similarly with the timed up and go test, there was a small decrease for the 65 to 75-year-olds and a much sort of greater substantial increase for the 85 and overs. Once again, being a 10-year difference, they started at a much worse level than the younger folks. And in terms of percentage, you can see here that there was a greater increase in muscular strength amongst the oldest old, and likewise there was a much greater decrease in the time taken to get up and go for the oldest of old. Now, of course, the question is, can you persuade someone over the age of 85 to partake in such a structured exercise regime? Now, that is sort of outside the scope of this paper, but still, this gives great hope for older people that as long as you start resistance exercising, even if you've never done it before, can be a substantial improvement in your muscular strength. And just as a bonus, we're going to briefly touch on a second paper, which you'll be able to find in the supplemental section under exercise. And this study was done in Chinese older frail adults over the age of 85, also took part in 12 weeks of resistance training under sort of different modalities, either high, either based on different levels of volume and different levels of intensity. And what they found, we're not going to sort of go into this paper here, it doesn't have sort of really nice graphs and or clear graphs, unfortunately. But what they found was that there was a dose dependent response. So the greater the volume and also the greater intensity resulted in a greater effect. So just looking at the results here, make this a bit bigger so you can see as well. So, the exercise volume of resistant training showed linear relationships with muscle strength of the lower limbs, 30 seconds sit to stand test. Again, you sit down and because how many times you can sit and stand up in 30 seconds, and the 6-minute walking test, how far you can walk in 6 minutes. And hold on, let's go to the conclusion. So, I'll just read the conclusion here. Resistance training was found to be associated with muscle strength and physical fitness in frail older adults in a dose-dependent manner. High-intensity resistance training could be more effective for improving the muscle strength of frail older adults, and the improvement in the 6-minute walk test performance was even higher. High-volume resistance training significantly improved muscle strength with even greater improvement in the 30-second sit to stand test and the 6-minute walking performances. So both intensity and volume of exercise were found to greatly value physical function in frail older adults. Low moderate intensity resistance training and low moderate volume resistance training also had some advantages in terms of safety, efficacy, and acceptance in a elderly with frailty. So just as you always hear, always ask your doctor first before partaking or starting an exercise regime. Starting at a more moderate low levels could be the stepping stone to sort of higher intensity and volume for people, especially if they are frail and over the age of 85. But again, positive that for both of these studies that older people over the age of 85, so the oldest old, can show a benefit from undertaking some resistance training. So obviously, same applies to people below that age, but this is a good result nonetheless. And with that, we've reached the end of this month's review. Hope you enjoyed it. Hope you found it interesting. And all I can ask is if please give a like to this video, subscribe to this channel if you would like to receive notifications of future videos. And just the final plug, the CLA is purely volunteer run. We have very little funds, so please visit our donation page, which you can also find a link below this video. And yes, even the smallest of small donations would make a big difference to us. Anyway, take care and see you next month. Goodbye.